Hi, this is the presentation for Sigmetrics for this paper called Multivariate Singular Spectrum Analysis and its Variance. My name is Anish Agarwal, and this is joint work with Abdullah Alamar and Debavat Shah, and it was done while we were at MIT. So the canonical problem we're going to try to tackle in this talk is of time series analysis. In particular, imagine you have data coming from a Poisson process, and you only get to observe integer observations as seen here. Here, the y-axis are different integer numbers, and the x-axis is this Poisson process developing over time. Okay. Given this kind of data, what we like to do is, can we recover the underlying mean from, and then forecast the underlying mean? Okay, those will be the two tasks that we focus on. A generic solution for this problem is something called singular spectrum analysis, or SSA for short. It's a very popular method in practice. It's a simple two-step procedure. The first step is you do a page matrix transformation, where you first take your time series, x1 to xt, capital T, and you create a matrix out of it as follows, where you take, say L is hyperparameter, you take the first L points of this time series, x1 XL, you put it as the first column, then the second L elements of this time series, x1 L plus 1 to x1 2L, the second column, and so on and so forth. That particular matrix is called the page matrix. Now, if you want to do imputation, you simply do some sort of singular value thresholding, or PCA, to get that imputation. So you take your ZX, you perform you find its SVD, you find a low rank approximation of it, and that's it for your estimation of its mean. If you want to forecast, you simply do linear regression between the last row of this matrix and the first L minus 1 rows. That gives you a linear model, and you can use that linear model to forecast in the future. Now, for the problem that we showed at the start of this talk, if you applied exactly the procedure we talked about in the previous slide, you see it works reasonably well, right? At least for imputation, it seems to be reasonably recovering the underlying mean, given just integer observations, mind you. And with forecasting, it's not working too great, but it's within the ballpark. Now, the question is one of the questions we wanted to answer is that, can we do better if we have access to many time series, such that the time series are somehow correlated? Okay. So now, instead of just having one time series, you have n time series. A simple solution to this problem is something called multivariate SSA, where you now take these n different time series and you create a page matrix out of all of them, and then you simply concatenate them column-wise. Okay. And then you perform the same two procedures afterwards, where you first do hard single value thresholding, or PCA, to do the imputation. And to learn a linear model, you learn one linear model across all of these different time series together. And you can see it works much, much better now. It seems to be predicting the mean really bang on target, given just, again, the integer observations. So that one step of using multiple time series together is helping with our imputation forecasting problem. Okay. You can see it's working a lot better than SSA. And surprisingly, it even works a lot better than state-of-the-art deep learning methods, such as deep AR, which has become an industry standard to do forecasting, at least. So the simple step of creating the page matrix, doing PCA, and then doing linear regression works really well, or is better than both SSA and state-of-the-art deep learning methods. So the key question we want to answer is, when does the simple method of MSSA work? And we'll provide one spatio-temporal factor model to reason about it. And under that factor model, we'll provide statistical guarantees. So here's the setup. So say you have n time series, and for them, you're getting observations in discrete time. So t is in the integer space. And for each x and t, you observe it with probability rho. So with probability rho, you observe fnt with the additional noise eta nt. And with probability 1 minus rho, you observe nothing. Okay, so you have noisy missing observations. And the goal is that, given x and t, to do imputation, that is, recover fnt for t in capital T, and to do forecasting, which is to forecast fnt for t greater than capital T. Okay, that's the formal setup. So here's the model, the spatio-temporal model. First, you want to somehow capture spatial structure across the different data points. And the way we do that is to say that f and t, each time series n at time point t, has a low rank representation. Okay, so there's a latent factor un associated with the nth time series. And there's a latent factor WT associated with the, or WR associated with the R fundamental time series. Now, if you want to, so this is just a low rank model that people study all the time in, say, matrix completion. But say now we also want to capture the temporal structure in the data. The way we do that is to say that WRT, that matrix, if you look at its Hankel matrix, that is low rank. Okay, and particular has rank less than G. Okay, so the FNT by itself, to capture spatial structure, we assume it has a rank R representation. And then the Hankel matrix induced by just the time series factor has a rank G approximation. It turns out that if you have such a spatio-temporal structure, then the stacked page matrix also has low rank. In particular, its rank is bounded by R times G. And this particular structure is really what motivates, this low rank structure of the stacked page matrix is really what motivates why this transformation is a good one. And it turns out the spatio-temporal factor model holds, at least approximately, in a wide variety of time series processes. For example, any sum of finite harmonics, which captures, say, seasonality, any polynomials and exponentials, any smooth periodic function. So any differentiable periodic function also has the spatio-temporal model holds for it, or any time series structure with a latent variable model structure. And further, we establish a Hankel calculus that says that of these various time series, they're closed under, that low rank structure is closed under addition element-wise multiplication. Okay, so it really is a very rich collection of time series that satisfy the spatio-temporal model. And you can see that the spatio-temporal model actually does hold, seems to hold in real world data. So the 3 different data sets that we played with, a financial data set, a traffic data set, electricity data set, which are some of the canonical data sets people study in the time series literature. And you can see that as the number of time series is increasing, that's given in the dotted orange line, the effective rank of the stacked page matrix remains extremely low. Right? So by this column-wise concatenation, it's not increasing the rank of the page matrix, but shows that indeed there is indeed a lot of correlation between these various time series. So what are our main results? What we show is that if the noise terms are independent sub-Gaussians and the spatio-temporal factor model holds for the mean of the multivariate time series, then with imputation, you get an error rate of something scaling as 1 over square root of min of n and t times t. If you just did SSA, you would get a rate of 1 over square root t. So this additional rate of min of n and t is what is given to you by MSSA, and that's what we see empirically why it's improving. So this is a theoretical representation of that phenomenon. With forecasting, we get a result that scales basically as 1 over square root min n t times t, but now at the top we have a max of 1 over and n and t. Okay, so if t is a lot bigger than n, you have the same rate as imputation. If n is a lot bigger than t, then the rate is weaker. But you can see that one simple way of dealing with the fact when you have n much larger than t is to simply create subsets of your time series such that of size t such that you effectively get back the same rate of 1 over square root min of n t times t. So those are the key results. Now let me show you some of the extensions we've done to the MSSA method. The first one is variance estimation. So say I want to estimate the variance of the noise term, the eta n square t. This is a simple 2-step procedure. The first is you do MSSA on the original time series. That gives you an estimate of the mean. The second step is you do a component-wise squaring of each element of the time series of the stacked page matrix. Then you do HSVT or hard signal value thresholding on that. And you can show that the mean of this time series is f squared plus sigma squared. Okay. And so now if you square the original time series you get from the first MSSA, and you subtract that from what you get from the component-wise squaring, you can see easily that the estimate you get is sigma hat squared. Okay, so this is the way to estimate time varying variance estimation, or like a Garch-like model. And again, so the type of result you can show is that if the noise terms are independent sub-Gaussians and the spatio-temporal factor model holds for both the mean and the variance of the multivariate time series, then the variance imputation scales as 1 over square root min of nt times t. And so here's an interesting example, some use case for it. So say you have data coming from just integer data. and you want to ask the question, was my data generated from a Poisson process? Okay, this is an important question to ask because a lot of the models that we build upon essentially make an assumption of a Poisson process. So does it actually hold in your data? So here we have data coming from a binomial process on the left and from a Poisson process on the right. Right? With the Poisson process, the mean and variance are the same. With the binomial process, they're different. And basically by applying the variance estimation algorithm and the mean estimation algorithm, we can verify whether the data we have comes from a Poisson or not. Right? On the left, you can see that there's indeed, it's accurately capturing both the latent mean and latent variance. On the right, we see that the latent mean and variance are approximately the same, which gives credence to the fact that it is indeed coming from a Poisson. Another extension we work on is what we call tensor SSA. So here, the algorithm is that you take the various time series, you create a page matrix out of it. Now, rather than doing a column-wise concatenation to get a longer page matrix, we actually stack them up in a third dimension to create a three-dimensional tensor. And then you can use tensor estimation techniques to estimate the means of this tensor. And you can see that for different relative scalings of n and t, we can see the effective, at least theoretically, the effective imputation recovery of TSSA versus MSSA versus matrix estimation. So when you have t being a lot larger than n, then in that case, MSSA wins. In particular, MSSA will have a rate scaling as 1 over squared nt. TSSA will have a rate of 1 over n squared. And matrix estimation, which is where you just do matrix completion or matrix estimation, the original time series of data, that will rate 1 over n. Now, if n is a lot larger than t, then actually they all give you the same theoretical rate, 1 over t. And this middle regime, where n is in between t to the cube and t, in that case, TSSA actually does the best. That's where you get a rate of 1 over squared, where TSSA gets a rate of 1 over min of n squared and t, and that's better than the other rates. And with that, we'd like to end. We have open source code available given here. And we've actually created a open source library where we implemented all these different time series algorithms at the database layer, and that can be found at tspdb.mit.edu. Thank you very much for your time.